Welcome to this video on applying Gauss's law for different spherical symmetries, and I'm going to come back and do some other ones in subsequent videos, other spherical symmetries, just to keep these a little bit shorter. And remember, we're looking at a method here, okay, for figuring out the electric field. And what we want to start to do now is look at what's the electric field inside a shape, right? And eventually we'll get to why is the electric field zero on the inside of a shell, okay? Well, over here I have a cloud of charge, and even though it looks a little darker in the middle, assume that the charge density, rho, right, because we're dealing with a volume charge density, is constant. All right, and so we could write that the total charge here, of course, is rho times V. I'm going to give you some dimensions on here. I'm going to say here's the center where r equals 0, and out here for the entire radius of the shape we have uppercase R. Now what I want to know is what is the electric field at a point, let's say right here. Okay, well I'm going to draw my Gaussian surface the way that I always would in order to do that. So I want to know the electric field here, and so I'm going to plot points where the electric field should be constant. Okay, so I'm going to plot these points in not my perfect circle here, but it does make a circular shape. Now keep in mind this is a cross section of a sphere. So we're seeing a circle, but it's really spherical. And I'm going to call the radius of the small Gaussian surface r, little r. Now we've already established what the electric field is if you could imagine all of this cloud out here not being present, the amount of enclosed charge on the inside, right, would be just the equation that we started with way back when. So if we look at that, right, if we use Gauss's law just to set that up, okay, so if I have E dot dA equals Q enclosed over epsilon naught, what I could show here is that E's constant everywhere on that surface, and the surface, once I integrate over all and add it all up, I get 4 pi r squared, because it is a spherical surface area, and that equals the amount of charge that's enclosed in the surface, not the entire charge on the outside here. And we can see again that we're going to have something that looks like Q enclosed over 4 pi epsilon naught times r squared. Okay, that's great. But how do we actually relate the amount of enclosed charge to the total amount of charge over here? We're going to use something a little bit different where we're going to do a ratio, and the ratio is going to be the amount of enclosed charge is equivalent to the amount of volume enclosed, right, or proportional to, excuse me, and the amount of total charge is going to be proportional to the total volume of the cloud. Okay, so what I'm doing now is I'm going to find an expression for Q enclosed that really is relating it to the entire cloud of charge and not just implying that it's just what's here on the inside. Okay, so Q enclosed, that's the thing we're going to solve for. V enclosed is 4/3 pi little r cubed, right, because that is the radius of the Gaussian sphere. And Q total is proportional to the total volume, which would be 4/3 pi big R cubed, because that is the total volume of the cloud. Now if I solve for Q enclosed, which I'm trying to get an expression for in terms of the total Q, what I end up with is the total charge times R cubed, little r cubed over big R cubed, right? The 4/3 pi would cancel once I multiply both over. So I have this expression. Now what I'm going to do with that expression is I'm going to plug this in over here, because what I want to do is I want to figure out what is the electric field at a point inside the shape, but in terms of the actual entire shape, just so we're not forgetting that. And so what I'm going to do next is I'm going to plug that in, and I'll go through the steps here just so that y'all can see the simplification. So I have Q total times little r cubed over big R cubed, that's the numerator of this, and then I have 4 4 pi epsilon naught times little r squared. Now, with some simplifications here, okay, this will move down to the denominator, and so I will have q total times little r cubed over 4 pi epsilon naught times big R cubed times little r squared. Apologize for that. Let's get rid of that and we'll fix it. Little r squared. Okay, so with some simplifications here, we see that what we're left with is q total times r over 4 pi epsilon naught times r cubed. Now in this situation, what we see is, I'm going to go ahead and actually write it this way, is that all of these things would be constant, right? The total charge is constant for the cloud, the total radius of the cloud is constant for this scenario, but this r value, right, the little spherical Gaussian surface could vary. And so what we see is that we actually have a function that is a linear function. So we have all of this, which would represent the slope times r. So if you were to graph the electric field as a function of r, and this is when r is less than or equal to big R, right, you would see that it's actually just a linear shape like this. Now once we hit the outside and we pick a point anywhere out here, then we would be treating this big blob of charge just as sort of as a point charge, and we would get an expression like this where we have the inverse squared relationship. So what happens is the function starts as a linear function where the electric field increases as we work our way outwards, which makes sense because I'm enclosing more and more and more charge, and then at a value of big R, the function switches to being an inverse squared relationship. So it's kind of interesting to look at this and to say, yeah, it makes sense that there'd be less electric field at that point than if I was enclosing the entire charge. And at that point, as I go further out, I'm no longer enclosing more charge. The amount of enclosed volume and therefore enclosed charge is the volume of the actual cloud. And so there's no more electric field that can be contributed, and it starts to drop off. The same thing can be done with gravity and with mass, where I can actually see that the further into the Earth's crust I am, the less gravitational force there is at that point because there's less enclosed mass. And we can take a look at that in a later video. When we come back in the next video, what I want to just do is look at a shell of charge and look at why, for a conductor, is the electric field zero, or how can we at least prove that with Gauss's law.